Hey folks, welcome back to another lesson, and this is getting quite exciting now because we're now going to look at some quantum mechanics. Okay, so some really weird and interesting effects coming up soon, folks. So first of all, photoelectric effect experiment. So describe the experiment photoelectric effect, state the main conclusions of the photoelectric effect experiment, and state that the photoelectric effect is evidence that light radiation can exist as a particle, basically. Okay. So first of all, a few things we need to introduce to you, and I can show this to you when we're in class, is something called a gold leaf electroscope. So this is what it looks like. It looks like some kind of weird kind of balance thing. And the key thing we're interested in here is a stem where you've got a metal plate and a gold leaf. And this is literally a very, very, very thin layer of gold. And it's called a gold leaf. And in this experiment, this photoelectric experiment, we charge the gold leaf with negative charge. Okay? Now, how do we do that? There's actually two ways you can charge a gold leaf electroscope, by contact or by induction. If we charge it by contact, then what happens is that to begin with, the gold leaf electroscope is neutral. So notice the gold leaf is lying vertically flat. We then put a negatively charged conductor onto the surface of the plate here, and that means the charge will pass onto the gold leaf. And because you've got negative charges all round, remember, like charges repel, so that makes the gold leaf rise up the way. When we take the conductor away, the charge remains in the gold leaf, and the gold leaf should stay kind of at that angle there. So that's what we mean by charging by contact. Charging by induction is a little bit trickier, but the idea here is, again, we use a negative conductor, and we basically move all the positive charge to the top of the plate and the negative charge to the bottom. And the reason for that is because the negative charge on the plate here will be repelled by the negative charge on the stick here. So that leaves your positive charge at the top and your negative charge at the bottom. Because this is all negatively charged, the leaf will rise up. So what you then do, and this is where it's a wee bit tricky, is without changing anything, you then earth the plate here. And the simplest way to do that is just touching it with your finger and allowing the negative charge to go from your finger to the ground. And then the leaf will actually go down. Now, the reason why it goes down is because all the negative charge has been removed and the positive charges are only on the top plate. So then when you remove your negative conductor there, the positive charge can then spread out throughout the whole gold leaf and you get it going back up again. Now, usually we do this with a piece of metal sink sitting on top of the actual electroscope. So here's the actual experiment. Now, don't worry about remembering how to charge a gold leaf electroscope. You won't really be asked about that. You will, however, be asked about what's on this slide. So I would make a note of what's on this slide. So the zinc metal is scrubbed with an abrasive, i.e. sandpaper. And the reason for this is because if you leave zinc metal lying around, it will tend to react with oxygen to form zinc oxide. And this zinc oxide acts as a layer, an insulating layer, that stops the light hitting the metal. So that's why we want to rub it with some sandpaper to reveal the zinc metal. Now, the negative flashy zinc metal is placed on top of a charged electroscope. In fact, we'd probably put the zinc metal on top of the electroscope and then negatively charge it. So that's the setup, and that's what you have to know. The reason why you know this is because this sometimes comes up as a problem-solving question. It might say, how could you improve the experiment? You can improve it by scrubbing the zinc metal so that you reveal the zinc metal to the light. Now, here's what we do during the experiment. So first of all, a red laser is shone on the metal, and what we find is that nothing happens. We then repeat this with lasers of greater energy. So energies that are bigger than red would be green and then blue. And what do you think happens? Well, again, nothing happens. So what do we conclude from that? We conclude that increasing the energy of radiation has no effect. So I would make a wee note of this slide as well. So a fair bit of writing in this lesson, I'm afraid. Now, if making the lasers more energetic doesn't have any effect, what if we try to increase the irradiance? Because if you think about it, irradiance is I is equal to P over A, isn't it? Right, so let's just write the equation down. I is equal to P over A. So what that means is, if we increase the irradiance and we're keeping the area of the light the same, then surely that means the power must increase. And if the power in must increase, remember, power is the energy per second transferred, that means we must be giving the zinc metal more energy, mustn't we? So first of all, we do the same thing. We shine a brighter laser that is red, and what we find is nothing happens. We then repeat this with lasers of greater energy, but also greater irradiance, and what do you think happens? Nothing happens again. So what do we conclude? We conclude that increasing the irradiance of radiation has no effect. So again, could you copy this slide down here? Now, finally, by this point, you might be getting sick and tired of this, but we do the same experiment again, but we use a UV lamp. So we shine a UV lamp onto the metal. Now, remember, UV is a smaller wavelength than visible light. Red, blue, and green are all visible light, so UV has a much smaller wavelength and a much higher frequency. And what we see is that the gold leaf drops. This suggests electrons are released, because remember, in this situation, it was negatively charged, and the only way you can get the gold leaf to drop is if you actually remove those electrons. The only way you can remove those electrons is if they're actually fired away into the air. So what do we conclude from this final part of the experiment? We conclude that electrons are ejected only with radiation of specific energy. So that's really, really important, this idea of a specific energy. So please make a note of this here. So in case you don't believe any of that, there is a really nice video demonstration where the person goes through the red, blue, green laser, and he actually does all three at the same time, and you can see nothing happens. And then he finally repeats it with a UV lamp, and you do see it happen. So please watch this video to convince yourself that it does happen in real life, and I've not just made it up. Okay, so summary of this, and this is what I would like to take away from the experiment, so please write this down. The photoelectric effect is when electrons are ejected from a metal only if incident radiation is of a sufficient frequency. So incident radiation just means the radiation that you shine on it. Remember, radiation can be anything from the electromagnetic spectrum, so it could be radio, microwaves, infrared, visible, gamma, X-rays, UV, etc. Increase the irradiance, i.e. the amount of light, has no effect. So even though you could fire more of that light onto it, it doesn't mean you're giving it more energy. It doesn't mean it's going to eject the electron. So the photoelectric effect is evidence that light exists as a particle. This is because the energy of the light depends on its frequency, which has a fixed value, i.e. 10 Hz, 30 Hz, 40 Hz. It's a well-defined value. And this is really, really weird because remember, previously we looked at light existing as a wave. In fact, we had an experiment called Young's double slit experiment that proved light exists as a wave. So we've now come up with a second experiment to say, actually, light doesn't exist as a wave, light exists as a particle. So how do we square the two together? So let's look at that in the next couple of slides. So first of all, can we explain the photoelectric effect using waves? Because if we can, then that means light must exist as a wave. So first of all, we have light exists as a wave. That's our principal idea. Now, the energy of the wave is given by the amplitude of the wave, isn't it? And we know that if we have several waves together, if they are in phase and coherent, what can happen? Okay, a wee bit of revision there for you. Remember, we can get constructive interference. Now, what happens in constructive interference? The waves combine to give you a bigger amplitude, don't they? Okay. Now, if they combine, it means the irradiance must be greater because the power of the waves is more. Because remember, the amplitude has got bigger, so that means the energy is bigger, so that means the irradiance has increased. And the greater the irradiance, the greater the energy. You would expect if you're firing more energy at the electrons, then they should fly off. However, the photoelectric effect only depends on the frequency of the wave. It doesn't matter what irradiance it is. It doesn't matter how many waves are hitting those electrons. It has no effect. So, as always, if the data doesn't agree with the theory, you've got to either assume the theory is either wrong or your data is wrong. Now, because people have done this experiment quite a lot, we know that the data is correct. So that must lead us to conclude that light can't exist as a wave, it exists as a particle. Okay, so wave theory, just to summarize that, wave theory cannot explain these phenomena. It suggests that the energy depends on the irradiance. According to wave theory, bright red light should work. However, it doesn't. So therefore, that means the wave theory explanation is wrong. So if you want, make a wee copy of this. Ignore the word intensity. That doesn't really need to be there at all. So how did scientists come across solve this problem? Well, there's lots of bits and pieces to this. First of all, Planck came along and said that light travels in tiny packets of energy called quanta. And because it's tiny packets, that means there's a fixed amount. So that's why he called it a quanta. A quanta literally means a small amount of something. Okay? The energy of each quanta is given by its frequency. So therefore it's fixed and specific. And so the equation that describes it is this one here. Energy is measured in joules. Planck's constant is measured in joules per second, and frequency is measured in hertz. Now, Planck's constant is a value that you need to know. If you can't remember it, it is in your data sheet. And as a result of this, Planck actually won the Nobel Prize in 1918. Now, ironically, it was Einstein who used Planck's idea to actually explain the photoelectric effect. And this was the thing that he actually won his Nobel Prize for, and not special or general relativity. So Einstein proposed that light exists as particles. Because they've got well-defined energies, that means they could exist as a lump of something, i.e. a particle. And he said that the energy is related to the frequency, E is equal to hf. So Einstein won the Nobel Prize in 1921 for his services to theoretical physics and especially for his discovery of the law of the photoelectric effect. Now, how can we explain this with a model? And this is actually a former past paper question. So one idea is you could imagine the coconuts are like electrons, and say we try and hit it with a beam of light. So for argument's sake, we try and hit it with some ping pong balls. Okay, we know that the ping pong balls can't knock the coconuts off. And even if we increase the number of ping pong balls, it's unlikely to knock the coconuts off. So that's a bit like us saying, well, we're going to try and shine some red light on to knock the electrons out. It doesn't work, so let's shine more red light on it. It still doesn't work. The only way we can knock these coconuts off effectively is if we use a bigger ball, say like a basketball. And there, the basketball is big enough to knock the coconuts off. So it's a bit like saying, if we knock the coconuts off with the right frequency, then we can get electrons emitted. So make sure you know how to do that explanation. Make sure you write something down so you can learn that kind of model answer, if you like. So hitting the coconuts with more particles doesn't mean it will knock it over. This explains why increasing the radiance has no effect. Okay, folks, and this is just a wee summary that I've written to you in case you find it quite tricky to summarise that. So coconuts are like the electrons. If we hit the coconuts with a ping pong ball, i.e. a small specific frequency, they can't knock the coconuts off. Increasing the number of ping pong balls hitting the coconut has no effect. This is just like increasing the brightness of our ray of light. However, if we hit it with a basketball, i.e. a bigger specific frequency, we can knock the coconuts off. So that means it has to be a specific frequency before we can knock the coconuts off. Can you think of any problems with this analogy? Okay, because it's not a perfect analogy. See if you can think of any issues with it. And that's the end of that lesson.